Chapter 5. Deep Breakthroughs. In January 2014, something unprecedented happened in the UK technology industry. Google acquired a small company in a deal that, while unremarkable by the otherworldly standards of Silicon Valley, was extraordinary by the standards of the UK's rather modest computer technology sector. The company they acquired was DeepMind, a startup company which at the time employed fewer than 25 people, for the reported sum of $650 million. At the time of acquisition, it looked from the outside as though DeepMind had no products, technology, or business plan. They were virtually unknown, even within the specialist area in which they had chosen to operate, AI. The acquisition of this tiny AI company for a huge sum made headlines. The world wanted to know who this mystery outfit were and why Google thought an unknown company could possibly be worth so much. Artificial intelligence was suddenly big news and big business. Interest in AI exploded. The press noticed the buzz, and stories about AI began to appear in the media daily. Governments across the globe also noticed and started to ask how they should respond. A string of national AI initiatives quickly followed. Technology companies scrambled to avoid being left behind, and an unprecedented wave of investment followed. While DeepMind was the highest-profile AI acquisition, there were many others. In 2015, Uber acquired no fewer than 40 researchers from Carnegie Mellon University's machine learning lab in a single deal. In less than a decade, AI had been transformed from a quiet backwater of computing into the hottest and most hyped area of science. The sudden sea change in attitudes to AI was driven by rapid progress in one core AI technology: machine learning. Machine learning is a subfield of AI, but for much of the last 60 years it had evolved on a separate path, and, as we will hear in this chapter, the relationship between AI and its suddenly glamorous offspring has at times been strained. In this chapter, we will hear how the 21st century machine learning revolution happened. We'll begin by briefly reviewing what machine learning is, and then look at how one particular approach to machine learning, neural networks, came to dominate. Like the story of AI itself, the story of neural networks is a troubled one. There have been 2 neural net winters, and as recently as the turn of the century, many in AI regarded neural networks as a dead or dying field. But neural nets ultimately triumphed, and the new idea driving their resurgence is a technique called deep learning. Deep learning is the core technology of DeepMind. I will tell you the DeepMind story and how the systems that DeepMind built attracted global adulation. But while deep learning is a powerful and important technique, it isn't the end of the story for AI. So just as we did with other AI technologies, we'll discuss its limitations in detail too. Machine learning, briefly. The goal of machine learning is to have programs that can compute a desired output from a given input without being given an explicit recipe for how to do this. An example is in order. One classic application of machine learning is text recognition, taking handwritten text and transcribing it. Here, the input is a picture of the handwritten text. The desired output is the string of characters represented by the handwritten text. Text recognition is hard, as any postal worker will tell you. We all write differently, and many of us write unclearly. We use pens that leak ink onto the paper, and the paper itself becomes dirty and battered. Returning to the discussion in Chapter 2, text recognition is an example of a problem for which we don't know how to come up with an appropriate recipe. It isn't like playing board games, where we have recipes that work in principle, but need heuristics to make them practical. We just don't know what a recipe for text recognition might be. We need something else entirely, which is where machine learning comes in. A machine learning program for text recognition would typically be trained by giving it many examples of handwritten characters, with each example labelled with the actual text that was written. Figure 7 on the attached PDF illustrates this. The type of machine learning we have just described is called supervised learning, and it illustrates a crucially important point. Machine learning needs data. Lots and lots of data. In fact, as we will see, the provision of carefully curated sets of training data was crucial to the current success of machine learning. When we train a machine learning program, we have to be very careful about the training data that we use. First, we can usually only train the program with a tiny fraction of the overall space of inputs and outputs. In our handwriting example, we can't show the program all possible handwritten characters. That's impossible. If we could train the program with the complete set of possible inputs, then there would be no need for any clever machine learning techniques. Our program could just remember each input and corresponding desired output. Whenever it was then presented with an input, all it would have to do would be to look up the corresponding output. This is not machine learning. So, a program will have to be trained using only a small part of the overall set of possible inputs and outputs. But if the training data set is too small, then the program may not have enough information to learn the desired mapping from inputs to outputs. Another fundamental problem with training data is called feature extraction. Suppose you are working for a bank, which wants a machine learning program that will learn to identify bad credit risks. The training data for your program will probably consist of lots of records of past customers, each customer record being labelled with whether that customer in fact turned out to be a good or bad risk. The customer record will typically include their name, date of birth, residential address, annual income, along with records of transactions, loans, corresponding repayments, and so on. These components are called the features that can be used for training. But does it make sense to include all these features in your training data? Some of them may be completely irrelevant to whether someone is a bad credit risk. If you don't know in advance which features are going to be relevant for your problem, then you might be tempted to include everything. But there is a big problem with this, called the curse of dimensionality. The more features you include, the more training data you are going to have to give the program, and the more slowly the program is going to learn. The natural response is to only include a small number of features in your training data. But this presents problems of its own. For one thing, you may accidentally omit features that are necessary for the program to be able to learn appropriately, the features that actually indicate a poor credit risk. For another, if you make a poor choice of which features to include, then you also run the risk of introducing bias into your program. For example, if the only feature that you decided to include for your bad risk program was the address of the customer, then this is likely to lead to the program learning to discriminate against people from certain neighborhoods. The possibility that AI programs may become biased, and the problems this raises, are explored in more detail later. In reinforcement learning, we don't give the program any explicit training data. It experiments by making decisions and receives feedback on those decisions as to whether they were good or bad. For example, reinforcement learning is widely used to train programs to play games. The program plays the game and gets positive feedback if it wins or negative feedback if it loses. The feedback it gets, whether positive or negative, is called the reward. The reward is taken into account by the program the next time it plays. If it receives a positive reward, then that makes it more likely to play the same way. A negative reward would make it less likely to do so. A key difficulty with reinforcement learning is that in many situations, rewards may be a long time in coming, and this makes it hard for the program to know which actions were good and which were bad. Suppose our reinforcement learning program loses a game. What does that loss tell it, or indeed us, about any individual move made during the game? Concluding that all the moves were bad would probably be an overgeneralization. But how does it, and how do we, know which were the bad moves? This is the credit assignment problem. So far, we have said nothing about how a program might learn. Machine learning as a field is as old as AI itself, and just as large. Many techniques have been proposed over the past 60 years. But the recent successes of machine learning have been based around one particular technique: neural networks, usually abbreviated to neural nets. Neural nets are in fact one of the oldest techniques in AI. They were part of the original proposal by John McCarthy for his AI summer school in 1956. But they have seen a huge resurgence of interest this century. Neural nets, as the name suggests, were inspired by the networks of nerve cells, neurons, that are found in the microstructure of the brain and nervous system. Neurons are cells that can communicate with each other in a simple way, through fibers in the brain called axons, to other neurons via junctions called synapses. Typically, a neuron receives electrochemical signals via its synaptic connections and, depending on the signals received, will generate an output signal that will in turn be received by other neurons via their synaptic connections. Crucially, the inputs that a neuron receives are differently weighted. Some inputs are more important than others, and some inputs may inhibit the neuron, preventing it from generating an output. In animal nervous systems, networks of neurons are massively interconnected. The human brain is made up of about 100 billion neurons, and neurons in the human brain typically have thousands of connections. The idea of neural nets in machine learning, then, is to use these kinds of structures in a computer program. After all, the human brain provides proof that neural structures can learn very effectively. Perceptrons, Neural Nets version 1. The study of neural networks had its origins in the work of US researchers Warren McCulloch and Walter Pitts in the 1940s. They realized that neurons could be modeled as electrical circuits, more specifically, simple logical circuits. And they used this idea to develop a straightforward but very general mathematical model of them. In the 1950s, this model was refined by Frank Rosenblatt in a neural net model that he called perceptrons. The perceptron model is significant because it was the first neural net model to actually be implemented and is still of relevance today. Rosenblatt's perceptron model is shown in Figure 8 on the accompanying material. The oval indicates the neuron itself. The arrows going into the oval correspond to the inputs of the neuron, corresponding to its synaptic connections, and the arrow coming out to the right indicates the output of the neuron, corresponding to an axon. In the perceptron model, each input is associated with a number called its weight. In Figure 8, the weight associated with input 1 is W1, the weight associated with input 2 is W2, and the weight associated with input 3 is W3. Each input to the neuron is either active or inactive. If an input is active, then it stimulates the neuron by the corresponding weight. Finally, each neuron has an activation threshold, which is another number written as T. The idea is that if the neuron is stimulated beyond its activation threshold, T, then it will fire, which means making its output active. In other words, we add together the weights of all the inputs that are active, and if the total meets or exceeds T, then the neuron produces an output. Of course, the neural nets that we see in nature contain many neurons and are arranged in much more complex patterns. Artificial neural networks are usually organized in layers, as shown in Figure 9 on the accompanying document, in what is known as a multi-layer perceptron. This network consists of 9 neurons arranged into 3 layers of 3 neurons each. Every neuron in each successive layer receives all the outputs from the layer preceding it. One immediate point to note is that even in this very small network, things have started to get complicated. We now have a total of 27 connections between neurons, each with their own weight, and all 9 neurons have their own activation threshold. Although multiple layers for neural nets were envisaged as far back as the work of McCulloch and Pitts, in Rosenblatt's time, attention was focused on networks with a single layer, for the simple reason that nobody had any idea how to train neural networks with more than one layer. The weights associated with each connection are crucial to the operation of a neural net. In fact, that is really all a neural net breaks down into, this list of numbers. For any reasonably sized neural network, it will be a long list of numbers. Training a neural network therefore involves finding appropriate numeric weights somehow. The usual approach is to adjust the weight after each training episode, trying to make the network correctly map inputs to outputs. Rosenblatt experimented with a few different techniques for doing this and found one for a simple perceptron model which he called an error correction procedure. Nowadays, we know that Rosenblatt's approach is guaranteed to work. It will always train a program correctly, but there is one very big caveat. In 1969, Marvin Minsky and Seymour Papert published a book entitled Perceptrons, in which they showed that there are quite dramatic limits to what single-layer perceptron networks can do. Minsky and Papert's book remains controversial even today. Theoretical results that demonstrated the fundamental limitations of certain classes of perceptron seem to have been taken to imply limitations for all neural network models. In particular, multi-layer perceptrons, of the type shown in Figure 9, are not subject to these limitations. However, at the time, nobody had any idea how to train a network with multiple layers. They were a theoretical possibility rather than a working reality. It would take 2 decades before the science was developed that made this possible. Research into neural nets declined sharply at the end of the 1960s in favor of the symbolic AI approaches championed by McCarthy, Minsky, Newell, and Simon. Ironically, this decline came only a few years before the onset of the AI winter that we heard about in Chapter 3. In 1971, Rosenblatt died in a sailing accident, leaving the neural nets community without one of its main champions. Perhaps had he survived, the history of AI might have been different, but following his death, research into neural nets went into abeyance for more than a decade. Connectionism. Neural Nets version 2. The field of neural nets was largely dormant until a revival began in the 1980s. The revival was heralded by the publication of a 2-volume book entitled Parallel Distributed Processing, or PDP for short. PDP provided much more general models of neurons than were provided by perceptron models, and these models, in turn, enabled probably the most important contribution of the new body of work, a technique called backpropagation, used for training multi-layer neural nets. As is often the case in science, backpropagation, often called backprop, seems to have been invented and reinvented a number of times over the years, but it was the specific approach introduced by the PDP researchers that definitively established it. The development of backprop and the other innovations introduced by the PDP community made possible a whole slew of applications for neural nets, which went far beyond the simple demonstrations of perceptron models of 20 years earlier. Interest in neural nets exploded, but the PDP bubble proved to be short-lived. By the mid-1990s, neural net research was once more out of favor. With hindsight, we can see that the wheels came off the PDP wagon not because of any fundamental limitations of the basic ideas, but for a much more prosaic reason. Computers of that time were just not powerful enough to handle the new techniques. And at the same time that advances in PDP seemed to be flatlining, other areas of machine learning seemed to be making rapid progress. Mainstream interest in machine learning began to turn away from neural models once again. Deep learning. Neural Nets version 3. By around 2005, neural net research was again back in favor, and the big idea that drove the third wave of neural net research went by the name of deep learning. I would love to tell you that there was a single key idea that characterizes deep learning, but in truth, the term refers to a collection of related ideas. Deep learning means deep in at least 3 different senses. Of these, perhaps the most important, as the name suggests, is simply the idea of having more layers. Each layer can process a problem at a different level of abstraction. Layers close to the input layer handle low-level concepts in the data, such as the edges in a picture. And as we move deeper into the network, we find more abstract concepts being handled. As well as being deep in the sense of more layers, deep learning was able to enjoy the benefits of having larger numbers of neurons. A typical neural network from 1990 might only have about 100 neurons. The human brain, you will recall, has about 100 billion. No surprise, then, that such networks are very limited in what they can achieve. A state-of-the-art neural net from 2016 would have about 1 million neurons, about the same number as a bee. Looking at the historical rate of increase in the number of neurons, we might expect to reach the same number of artificial neurons as a human brain in about 40 years or so. That does not mean, though, that artificial neural nets will achieve human-level intelligence in 40 years, because the brain is not simply a big neural network. It also has structure. Finally, deep learning uses networks that are deep in the sense that the neurons themselves have many connections. In a highly connected neural network from the 1980s, each neuron might have 150 connections with other neurons. A neuron in a state-of-the-art neural network at the time of writing would have about as many connections as there are in a cat brain. A human neuron has on average about 10,000. So, deep neural networks have more layers and more better-connected neurons. To train such networks, techniques beyond backprop were needed, and these were provided in 2006 by Geoff Hinton, a British-Canadian researcher who, more than anyone else, is identified with the deep learning movement. Hinton is a remarkable individual. He was one of the leaders of the PDP movement in the 1980s and one of the inventors of backprop. What I find personally so remarkable is that Hinton didn't lose heart when PDP research began to lose favour. He stuck with it and saw it through to its next incarnation in the form of deep learning, for which he has received international acclaim. Hinton is also, as it happens, the great-great-grandson of George Boole, whom we met in Chapter 3 as one of the founders of modern logic, although, as Hinton has pointed out, that is probably the only thing that connects him to the logical tradition in AI. Deeper, bigger, more interconnected neural nets were one key ingredient in the success of deep learning, and work by Hinton and others on new techniques for training neural nets was another. But there were two further ingredients required to make deep learning a success: data and computer power. The importance of data to machine learning can be illustrated no better than by the story of the ImageNet project. ImageNet was the brainchild of Chinese-born researcher Feifei Li. Born in Beijing in 1976, Li moved to the United States in the 1980s and studied physics and electrical engineering. She joined Stanford University in 2009 and headed the AI lab at Stanford from 2013 to 2018. Li's insight was that the entire deep learning community would benefit from having large, well-maintained datasets that would provide a common baseline against which new systems could be trained, tested, and compared. To this end, she started the ImageNet project. ImageNet is a large online archive of images, about 14 million images at the time of writing. The images themselves are nothing more than photographs that you can download in common digital formats such as JPEG. Crucially, though, the images have been carefully classified into 22,000 different categories using an online thesaurus called WordNet, which contains a large number of words that have been carefully arranged into categories. For example, identifying words that have the same or opposite meanings, and so on. Looking into the ImageNet archive now, I can see it has about 1,032 pictures in the category of volcanic crater and about 122 pictures in the category of frisbee. The eureka moment for image classification came in 2012, when Geoff Hinton and two colleagues, Alex Krzyzewski and Ilya Suskeva, demonstrated a system called AlexNet, a neural net that dramatically improved performance in an international image recognition competition based on ImageNet. The final ingredient required to make deep learning work was raw computer processing power. Training a deep neural net requires a huge amount of computer processing time. The work that needs to be done in training is not particularly complex, but there is an enormous amount of it. For all their undoubted successes, deep learning and neural nets suffer from some well-publicized drawbacks. First, the intelligence they embody is opaque. The expertise that a neural network has captured is embodied in the numeric weights associated with the links between neurons, and as yet we have no way of getting at or interpreting this knowledge. A deep learning program that tells you it sees cancerous tumors in an X-ray scan cannot justify its diagnosis. A deep learning program that declines a bank loan for a customer cannot tell you why it does so. In Chapter 3, we heard that expert systems like Mycin were capable of a crude form of explanation, retracing the reasoning that was used to reach a conclusion or recommendation, but neural networks are not even capable of this. There is a lot of work underway currently to try to deal with this issue, but at present we have no idea how to interpret the knowledge and representations that neural networks embody. Another key problem for deep learning is that, in a subtle but very important way, neural networks are not robust. For example, it is possible to make subtle changes to images which are undetectable to humans, but which result in neural nets completely misclassifying them. Figure 10 on the accompanying PDF illustrates this. On the left is the original image of a panda. On the right, a doctored image. I hope you will agree that the two images appear to be the same, and in particular, they both seem to be pictures of a panda. While a neural net correctly classifies the image on the left as a panda, the image on the right is classified as a gibbon. The study of these issues is known as adversarial machine learning. The terminology arises from the idea that an adversary is deliberately trying to obfuscate or confuse the program. While we might not be overly concerned if our image classification program incorrectly classified our collection of animal images, adversarial machine learning has thrown up much more disturbing examples. For example, it turns out that road signs can be altered in such a way that while a human has no difficulty interpreting them, they are completely misunderstood by the neural nets in a driverless car. Before we can use deep learning in sensitive applications, we need to understand these problems in much more detail. Deep Mind. The story of Deep Mind, which I referred to at the start of this chapter, perfectly epitomizes the rise of deep learning. The company was founded in 2010 by Demis Hassabis, an AI researcher and computer games enthusiast, together with his school friend and entrepreneur, Mustafa Suleyman. And they were joined by Shane Legg, a computational neuroscientist that Hassabis met while working at University College London. As you heard earlier, Google acquired DeepMind early in 2014. I can recall seeing stories in the press about the acquisition and starting in surprise when I saw that DeepMind were an AI company. It was obvious at the time of the acquisition that AI was big news again, but the idea that there was an AI company in the UK that I had never heard of, that was worth apparently $650 million, was utterly bewildering. Along with many others, I immediately went to the DeepMind website, but frankly it didn't give me much more information. There were no details at all about the company's technology, products, or services. It did, however, present one rather intriguing tidbit. The publicly stated mission of DeepMind, it said, was to solve the puzzle of intelligence. I've already mentioned that the wildly varying fortunes of AI over the past 60 years have taught me to be wary of ambitious predictions about progress in AI. You can imagine how startled I was to see such a bold statement from a company that had just been acquired by one of the world's technology giants. But the website offered no more detail, and I could find nobody who knew any more than I did. Most colleagues in AI regarded the announcement with skepticism, possibly tinged with a little professional jealousy. I heard little more about DeepMind until later that year, when I happened to meet my colleague Nando de Freitas. Nando is one of the world leaders in deep learning, and at the time he was a professor alongside me at Oxford University. He later left to work with DeepMind. He was on his way to a seminar with his students, and under his arm he was clutching a pile of scientific papers. He was obviously excited about something. He told me, "This group in London, they've trained a program to play Atari video games from scratch." I have to say, at first I was not impressed. Programs that can play video games are nothing new. It's the sort of challenge we might give to an undergraduate student as a project, which is what I told Nando. So he patiently explained what was going on, and then I understood why he was so excited, and it slowly began to dawn on me that we really were entering a new era of AI. The Atari system that Nando referred to was the Atari 2600 game console dating from the late 1970s. The Atari 2600 was one of the first successful video game platforms. It supported video at the grand resolution of a 210 by 160 pixel grid with up to 128 different colors. User input was through a joystick equipped with a single fire button. The platform used plug-in cartridges for game software, and the version that DeepMind used had 49 games in total. They described their aim as follows. Our goal is to create a single neural network agent that is able to successfully learn to play as many of the games as possible. The network was not provided with any game-specific information or hand-designed visual features, and was not privy to the internal state of the emulator. It learned from nothing but the video input, the score, and the set of possible actions, just as a human player would. To understand the significance of DeepMind's achievement, it is important to understand what their program did and didn't do. Perhaps most important, nobody told the program anything at all about the games it was playing. If we were trying to build an Atari playing program using knowledge-based AI, then the way we would probably proceed would be by extracting knowledge from an expert Atari player and trying to encode it using rules or some other knowledge representation scheme. Good luck with that if you want to try. But DeepMind's program was given no knowledge about the game at all. The only information the program was given was the image that would appear on the screen and the current score of the game. That was it. The program had nothing else to go on whatsoever. What is particularly significant here is that the program was not given information such as object A is at location (x, y). Any information like this would have to be somehow extracted from the raw video data by the program itself. The results were remarkable. The program taught itself to play using reinforcement learning, playing a game repeatedly, experimenting in each game and getting feedback, and learning which actions led to rewards versus those that didn't. The program learned to play 29 of the 49 games at above human-level performance. With some games, it achieved superhuman levels of performance. One game in particular attracted a lot of interest. The game of Breakout was one of the first video games to be developed in the 1970s. It involves the player controlling a bat, which is used to bounce a ball up to a wall which is made up of coloured bricks. Every time the ball hits a brick, the brick is destroyed, and the goal is to destroy the whole wall as quickly as possible. Figure 11 on the accompanying PDF shows the program at an early stage of learning to play. After it has played the game about 100 times, at this stage it misses the ball frequently. After a few hundred more training rounds, the program becomes expert. It doesn't ever miss the ball. And then something remarkable happened. The program learned that the most efficient way to accumulate points was to drill a hole down the side of the wall so that the ball was above the wall. The ball would then quickly bounce between the wall and the top barrier, without the player having to do anything, shown in Figure 12 on the accompanying file. This behavior was not anticipated by DeepMind's engineers. It was autonomously learned by the program. The video of the game is readily available online. I have used it in my lectures dozens of times. Every time I show the video to a new audience, there is an audible gasp of amazement as the audience understands what the program had learned to do. If their Atari playing program was the only thing that DeepMind had ever accomplished, then they would have earned a respectable place in AI history. But the company followed it up with a further series of successes. The most famous of these, and at the time of writing, probably still the most famous AI system built to date, was called AlphaGo. It was a program to play the ancient Chinese board game Go. Go is an intriguing target for AI. The rules of Go are extremely simple, much simpler than chess, for example. And yet, in 2015, Go-playing programs were well below the level of human expert performance. So, why was Go such a difficult target? The answer is simply that the game is big. The board is a 19 by 19 grid, giving a total of 361 places where pieces may be laid. Chess is played on an 8 by 8 grid, with therefore only 64 places for pieces. As we heard in Chapter 2, the branching factor for Go, the average number of moves available to a player at any given point in the game, is about 250, while chess has a branching factor of about 35. In other words, Go is much larger than chess in terms of its board size and branching factor. And games of Go can last for a long time. 150 moves in one game is common. AlphaGo used two neural networks. One, the value network, was solely concerned with estimating how good a given board position was, while another, the policy network, made recommendations about which move to make based on a current board position. The policy network contained 13 layers and was trained by using supervised learning first, where the training data was examples of expert games played by humans, and then reinforcement learning based on self-play. Finally, these two networks were embedded in a sophisticated search technique called the Monte Carlo tree search. Before the system was announced, DeepMind hired Fan Hui, a European Go champion, to play against AlphaGo. The system beat him 5-0. This was the first time a Go program had beaten a human champion player in a full game. Shortly after, DeepMind announced that AlphaGo was going to be pitted against Lee Sedol, a world champion Go player in a 5-match competition to be held in Seoul, Korea, in March 2016. The science of AlphaGo is fascinating, and AI researchers, myself included, were intrigued to see what would happen. For the record, my guess was that AlphaGo might win 1 or 2 matches at most, but that Sedol would decisively win the competition overall. What none of us expected was the completely unprecedented wave of publicity that surrounded the competition. The event made headlines across the world, and the story of the competition was even made into a feature film. In the event, AlphaGo beat Lee Sedol 4-1. Lee lost the first 3, came back to win the 4th, but lost the 5th. By all accounts, Lee was stunned to lose the first game. He expected to win easily. More than one person joked at the time that AlphaGo deliberately lost the 4th match so that Lee wouldn't feel so bad. At various points in the competition, human commentators remarked on what seemed to be strange moves made by AlphaGo. They were, apparently, not the kind of moves that a human would make. Of course, when we try to analyze how AlphaGo played, we do so from a very human standpoint. We instinctively look for the kind of motives and strategies that we would use when we play the game. We anthropomorphize. Trying to understand AlphaGo in this way is pointless. AlphaGo is a program that was optimized to do one single thing: to play the game of Go. We want to attribute motives and reasoning and strategy to the program, but there are none of these. AlphaGo's extraordinary capability is captured in the weightings in its neural nets. These neural nets are nothing more than very long lists of numbers, and we have no way of extracting or rationalizing the expertise that they embody. One might think that 2 landmark achievements were enough, but just 18 months later, DeepMind were in the news again, this time with a generalization of AlphaGo called AlphaGo Zero. The extraordinary thing about AlphaGo Zero is that it learned how to play to a superhuman level without any human supervision at all. It just played against itself. To be fair, it had to play itself a lot, but nevertheless it was a striking result, and it was further generalized in another follow-up system called AlphaZero, which learned to play a range of other games, including chess. After just 9 hours of self-play, AlphaZero was able to consistently beat or draw against Stockfish, one of the world's leading dedicated chess-playing programs. The exciting thing here was the generality of the approach. AlphaGo could only play Go, and for all its cleverness at this, it had required considerable effort to build the system specifically for that. AlphaZero, it seemed, could be turned to many different types of board games. Of course, we need to be careful not to read too much into these results. For one thing, although AlphaZero embodies an impressive degree of generality, it is a far more general expert game-playing program than any other program before it. It does not in itself represent a major advance toward general intelligence. It doesn't even remotely have the same kind of generality of intelligent capabilities that we all have. It can play board games superbly, but it can't converse, or make a joke, or cook an omelette, or ride a bicycle, or tie a pair of shoelaces. Its remarkable abilities are still actually very narrow. And of course, board games are highly abstract. They are a long way from the real world, as Rodney Brooks would be quick to remind us. Toward general AI, deep learning has proved to be enormously successful, in the sense that it has enabled us to build programs that we could not have imagined a few years ago. But laudable as these achievements genuinely are, they are not a magic ingredient that will propel AI toward the grand dream. Let me try to explain why. To do this, we'll look at 2 widely used applications of deep learning techniques: image captioning and automated translation. In an image captioning problem, we want a computer to be able to take an image and give a textual description of it. Systems that have this capability to some degree are now in widespread usage. The last update of my Apple Mac software gave me a photo management application that does a decent job of being able to classify my pictures into categories like beach scene, party, and so on. At the time of writing, several websites are available, typically run by international research groups, which allow you to upload photos and will attempt to provide captions for them. To better understand the limitations of current image captioning technology, and hence deep learning, I uploaded a family picture to one, in this case Microsoft's Caption Bot. The photo is shown in Figure 13 on the accompanying document. Before examining Caption Bot's response, pause for a moment to look at the picture. If you are British or a fan of science fiction, then you will very probably recognize the gentleman on the right of the picture. He is Matt Smith, the actor who played the eponymous Doctor Who from 2010 to 2013 in the BBC television show. You won't recognize the gentleman on the left. He is my late grandfather-in-law. Caption Bot's interpretation of the picture was as follows. I think it's Matt Smith standing posing for a picture, and they seem smiley face, smiley face. Caption Bot correctly identified a key element of the picture and went some way to recognizing the setting: standing, posing for a picture, smiling. However, this success can easily mislead us into thinking that Caption Bot is doing something that it most certainly is not, and what it is not doing is understanding. To illustrate this point, think about what it means for the system to identify Matt Smith. As we saw previously, machine learning systems like CaptionBot are trained by giving them a very large number of training examples, each example consisting of a picture together with a textual explanation of the picture. Eventually, after being shown enough pictures containing Matt Smith, together with the explanatory text, Matt Smith, the system is able to correctly produce the text, Matt Smith, whenever it is presented with a picture of the man himself. But CaptionBot is not recognizing Matt Smith in any meaningful sense. To understand this, suppose I asked you to interpret what you see in the picture. You might come back with an explanation like this. I can see Matt Smith, the actor who played Doctor Who, standing with his arm around an older man. I don't know who he is. They are both smiling. Matt is dressed as his Doctor Who character, so he is probably filming somewhere. In his pocket is a rolled-up piece of paper, so that is likely to be a script. He is holding a paper cup, so he is probably on a tea break. Behind them, the blue box is the TARDIS, the spaceship/time machine that Doctor Who travels around in. They are outdoors, so Matt is probably filming on location somewhere. There must be a film crew, cameras and lights somewhere close by. CaptionBot wasn't able to do any of that. While it was able to identify Matt Smith in the sense of correctly producing the text Matt Smith, it wasn't able to use this to then interpret and understand what is going on in the picture. And the absence of understanding is precisely the point here. Apart from the fact that systems like CaptionBot only have a limited ability to interpret the pictures they are shown, there is another sense in which they do not, and currently cannot, demonstrate understanding of the kind that we can. When you looked at the picture of Matt Smith dressed as Doctor Who, you would probably have experienced a range of thoughts and emotions above and beyond simply identifying the actor and interpreting what was going on. If you were a Doctor Who fan, you might have found yourself reminiscing fondly about your favourite episode of Doctor Who with Matt Smith in the title role, The Girl Who Waited, I hope we can all agree. You might have remembered watching Matt Smith as Doctor Who with your parents or your children. You might have remembered being scared by the monsters in the programme, and so on. It might remind you of an occasion where you were on a film set or saw a film crew. Your understanding of the picture is therefore grounded in your experiences as a person in the world. Such an understanding is not possible for CaptionBot because CaptionBot has no such grounding, nor, of course, does it purport to. CaptionBot is completely disembodied from the world, and as Rodney Brooks reminded us, intelligence is embodied. I emphasize that this is not an argument that AI systems cannot demonstrate understanding, but rather that understanding means more than being able to map a certain input, a picture containing Matt Smith, to a certain output, the text Matt Smith. Such a capability may be part of understanding, but it isn't by any means the whole story. Automated translation from one language to another is another area in which deep learning has led to rapid progress over the past decade. Looking at what these tools can and cannot do helps us to understand the limitations of deep learning. Google Translate is probably the best-known automated translation system. Originally made available as a product in 2006, the most recent versions of Google Translate use deep learning and neural nets. The system is trained by giving it large volumes of translated texts. Let's see what happens when the 2019 iteration of Google Translate is given an unreasonably difficult problem. Translating the first paragraph of À la recherche de temps perdu, In Search of Lost Time, the classic early 20th century novel by the French author Marcel Proust. Here is the first paragraph in the original French. Longtemps je me suis couché de bonne heure. Parfois, à peine ma bougie éteinte, mes yeux se fermaient si vite que je n'avais pas le temps de me dire « Je m'endors ». Et une demi-heure après, la pensée qu'il était temps de chercher le sommeil m'éveillait. Je voulais poser le volume que je croyais avoir encore dans les mains et souffler ma lumière. Je n'avais pas cessé en dormant de faire des réflexions sur ce que je venais de lire. Mais ces réflexions avaient pris un tour un peu particulier. Il m'est semblé que j'étais moi-même ce dont parlait l'ouvrage. Une église, un quatuor, la rivalité de François Ier de Charles le Quint. I'm embarrassed to say that despite the decade-long efforts of a hard-working group of language teachers, I understand very little French. I can make out only the odd isolated phrase in that text, and without help, I have no sense whatsoever of what the entire text means. Here is that first paragraph, translated into English by writer and translator C.K. Scott Moncrief. His translation of À la recherche du temps perdu is one of the most celebrated translations in literary history. His translation is regarded as a masterpiece, although it has been criticized for taking liberties with Proust's language. For a long time, I used to go to bed early. Sometimes, when I had put out my candle, my eyes would close so quickly that I had not even time to say, "I'm going to sleep." And half an hour later, the thought that it was time to go to sleep would awaken me. I would try to put away the book, which I imagined was still in my hands, and to blow out the light. I had been thinking all the time, while I was asleep, of what I had just been reading, but my thoughts had run into a channel of their own, until I myself seemed actually to have become the subject of my book. A church, a quartet, the rivalry between Francois I and Charles V. Much better. But interestingly, although this is beautifully written English, the meaning is still not completely transparent, not to me at least. What does the author mean when he writes, "I seemed actually to have become the subject of my book"? A church, a quartet, the rivalry between Francois I and Charles V. How can you become a church? What does he mean by a quartet? What rivalry between Francois I and Charles V is he referring to? And for someone that uses electric lighting, what does it mean to blow out a light? Now let's see what Google Translate made of it. Long time, I went to bed early. Sometimes, when my eyes would close so quickly that I had no time to say, "I fall asleep." And half an hour later, the thought that it was time to go to sleep would awaken me. I wanted to ask the volume that I thought I had in my hands and blow my light. I had not ceased while sleeping to reflections on what I had read, but these reflections had taken a rather peculiar turn. I felt that I myself was what spoke the book, a church, a quartet, the rivalry between Francis I and Charles V. This is recognizably the same text as the professional translation, and so Google Translate is doing something sophisticated. But you don't have to be a professional translator or an expert on literature to see its limitations. The expression, "blow my light," makes no sense in English, and the sentences that follow don't make sense either. Indeed, they're rather comical, and the translation includes phrasings that a native English speaker would never use. The overall impression that we are getting is of a recognizable but unnaturally distorted version of the text. Of course, we gave Google Translate an unreasonably difficult problem. Translating Proust would be a huge challenge even for a professional French-to-English translator. So why is this? And why is it so hard for automated translation tools to tackle? The point is that a translator of Proust's classic novel requires more than just an understanding of French. You could be the most competent reader of French in the world and still find yourself bewildered by Proust, and not just because of his frankly exhausting prose style. To properly understand Proust, and hence to properly translate Proust, you also need to have a great deal of background knowledge. Knowledge about French society and life in the early 20th century. For example, you would need to know they used candles for lighting. Knowledge of French history, of François I and Charles V and the rivalry between them, knowledge about early 20th century French literature, the writing style of the time, allusions that authors might make, and knowledge about Proust himself, what were his main concerns. A neural net of the type used in Google Translate has none of that. This observation, that to understand Proust's text requires knowledge of various kinds, is not a new one. We came across it before in the context of the Psych project. Remember that Psych was supposed to be given knowledge corresponding to the whole of consensus reality, and the Psych hypothesis was that this would yield human-level general intelligence. Researchers in knowledge-based AI would be keen for me to point out to you that decades ago they anticipated exactly this issue. The sharp retort from the neural nets community would then be that the techniques proposed by the knowledge-based AI community didn't work out so well, did they? But it is not obvious that just continuing to refine deep learning techniques will address this problem. Deep learning will be part of the solution, but a proper solution will, I think, require something much more than just a larger neural net, or more processing power, or more training data in the form of boring French novels. It will require breakthroughs at least as dramatic as deep learning itself. I suspect those breakthroughs will require explicitly represented knowledge as well as deep learning. Somehow, we will have to bridge the gap between the world of explicitly represented knowledge and the world of deep learning and neural nets. The Great Schism. In 2010, I was asked to organize one of the big international AI meetings, the European Conference on AI, ECAI, which was to be held in Lisbon, Portugal. Attending conferences like ECAI is an important part of the life of an AI researcher. We write up our research results and submit them to the conference, where they are reviewed by a program committee, a group of eminent scientists who decide which of the submissions deserve to be heard at the conference. Good conferences in AI only accept about 1 in 5 submissions, so having a paper accepted is very prestigious. The really big AI conferences attract more than 5,000 submissions. So you can imagine I felt very honored to be asked to chair the ECAI. It's an indication that the scientific community trusts you. And it is the sort of distinction that academics mention when they apply for a pay rise. My job as chair included assembling the program committee, and I was keen to include a good representation from the machine learning community. But something unexpected happened. It seemed that every machine learning researcher I invited said no. It isn't unusual to be politely rebuffed when you are trying to persuade people into a role like this. After all, it is a lot of work. But it seemed I couldn't get anyone from machine learning to sign up. Was it me, I wondered? Or ECAI? Or what? I sought advice from colleagues who had organized the event previously, and others who had experience of other AI events. They reported similar experiences. The machine learning community, it seemed, just wasn't very interested in the events that I thought of as, well, mainstream AI. I knew that the 2 big scientific events for the machine learning community were the Neural Information Processing Systems, NeurIPS, conference, and the International Conference on Machine Learning, ICML. Most subfields of AI have their own specialist conferences, so the fact that this community's attention should be focused on those was not surprising. But until then, it hadn't quite dawned upon me that many in the machine learning community simply don't define themselves as being part of AI at all. With hindsight, the schism between AI and ML seems to have started very early on, perhaps with the publication by Minsky and Papert of their 1969 book, Perceptrons, which, as we saw earlier, seems to have played a role in killing off neural AI research from the late 1960s until PDP emerged in the mid-1980s. Even in the present day, more than half a century later, there is still bitterness about the consequences of that publication. Whatever the origins of the schism, the truth is that at some point, many in the machine learning research area diverged from mainstream AI, and took off on their own trajectory. While there are certainly many researchers who see themselves as comfortably straddling the fence between machine learning and artificial intelligence, many machine learning experts nowadays would be surprised and possibly irritated to have the label AI attached to their work, because for them, AI is the long list of failed ideas that I've referenced elsewhere in this book.